At this point, I'm sure there's quite a few out there that are thinking that all this looks like a terrible idea. We started off complaining that we had problems trusting just one bank, and now we're proposing a design where anyone can join anonymously over the internet. How on earth can we trust that the ledger is going to be maintained in ways that everybody agrees are honest and in keeping with the agreed rules? Hey everyone, this video is sampled from my online course which teaches you tokenomics for fundraising. You'll learn about the fundraising process, key tokenomic concepts, and get a complete spreadsheet model that you'll learn how to use by solving real-world fundraising problems. You can find the link to the full course in the description section below. And if you'd like to support this channel and help me to create more free content, please like, share, subscribe, and hit that notification bell. That's all. Now back to the video. We should take the security concerns seriously and ask, what else can we do about them? It's probably not a massive spoiler at this point to tell you that blockchains give us an alternative solution. But to explain how, we're going to have to sketch out some of the technical details of how they work. So get ready, because this is going to be quite the ride. The first defining feature of a blockchain is that its ledger maintenance activities are no longer limited to a single agent or small group. They are now shared by a much larger number of agents. This maintenance is performed by giving each one of these agents their own locally stored copy of the ledger. Each of these copies is synchronized with all the others to maintain identical data, a shared state. That's done by each of these agents running a special piece of software that stores the local ledger copy and performs the calculations and data processing necessary to maintain this correctly synchronized shared state. Each instance of these software operations connects and communicates with all the others. So together, these guys form a network, and each one of these points of connection and communication within that network is known as a node. And so what we have here is a simplified illustration of a distributed ledger design. We can contrast that visually with the centralized database design that is normally used to store and manage digital ledger data. It's worth noting that the distributed state of the ledger is one feature that contributes to blockchain data security. By giving each node their own copy of the ledger, this raises the difficulty of making an attack on its data, since that attack now has to be replicated on every ledger stored on every node in this network. But this distributed digital ledger design is not quite yet a blockchain, because we're still missing an element of decentralized control. This trips quite a few people up, but distributed ledgers and decentralized ledgers are not the same thing. Let's see why. Assume that in this picture, every node here has their own copy of the ledger, so it's distributed. But only these nodes at the top have permission to write new transactions to the ledger. Or perhaps there's another agent outside here who gets to choose which nodes are given those writing privileges over the long term. Hopefully, these examples help make clear that distributed ledgers are not necessarily decentralized, and that the words distributed and decentralized do not mean the same thing. In order to be decentralized, there needs to be no limitations placed on who can become a new node in the network. Anyone must be able to join and store their own copy of the ledger and have full permission to write to it and maintain it, with no variation in the rules and privileges between nodes for performing these tasks. Put another way, no one must need permission to become a node. And this is the crucial feature that distinguishes blockchains from a larger group of distributed ledger designs. In blockchains, participation in the processes that validate and process new data transactions are permissionless. But even then, you need to be careful. Permissionless validation is not a guarantee of decentralization. It only makes decentralization possible. Consider a permissionless network which has all the nodes being run by one person, or a network which has all the nodes being run by different people but out of a single computer. In both of these examples, we don't have decentralized control. Whether decentralization is actually achieved will depend on who joins the network and how independent all those agents really are from each other. Regardless, permissionless validation is a necessary prerequisite for decentralization, and it also creates the possibility for a centralized network to become decentralized over time. Now, at this point, I'm sure there's quite a few out there that are thinking that all this looks like a terrible idea. We started off complaining that we had problems trusting just one bank, and now we're proposing a design where anyone can join anonymously over the internet. How on earth can we trust that the ledger is going to be maintained in ways that everybody agrees are honest and in keeping with the agreed rules? It looks like this decentralized design is making our trust problem worse, not better. The solution to this lies in the final key component of a blockchain's design, the consensus mechanism. This feature is so named because it describes a process that only allows ledger data to be changed when there is agreement or consensus among a large share of all the nodes on a blockchain network. This ensures that real, valid transactions are executed and that everyone syncs up their local copies of the ledger according to a consensually shared truth. So, how do consensus mechanisms work? Well, it isn't easy to explain, especially when you get into the deeper technical details. We would need more than just a few more long videos to do that. Right now, we're focusing on explaining blockchain as it matters to business. So we're just going to stick to a higher level overview that covers the key points and highlights the economic benefits. In those high-level terms, we can say that consensus mechanisms solve our trust problem by making many bad actor behaviors impossible to begin with. That doesn't happen by magic. Consensus mechanisms typically involve a combination of design elements that are informed by game theory and by cryptography. In the first case, actions, rewards, penalties, and information revelation are designed so that they make bad behaviors economically impossible to execute, requiring billions of dollars in capital, for example. And in the latter case, codes with special mathematical properties are used that would take eons to crack with our best computer technology. Now, it's worth our while to go into one detail of how cryptography is used. When members of the network post new ledger transactions, these are batched into blocks. Each new block is then chained to the one that came before it using a special cryptographic code. This code has a unique relationship between the new block and the one that came before it, and that relationship is also unique to all the transactions that are contained in both of these blocks. And that tells you where the terms blockchain, cryptocurrency, and crypto come from. To tamper ledger data that is structured in this way, you now need to crack the cryptographic codes for a chosen block, and because each of those codes also depends on the transaction content of its block, you would then need to crack the codes for all the blocks that come after it. Cracking just one of those codes requires more computational capacity than exists in the entire world being run for multiple human lifetimes. It is these mathematically provable properties that create consensus around the status of historical chain data and create trust in the system, even when the data has been processed and stored by multiple anonymous and unrelated agents. Let's take a moment to digest what we have just covered. Blockchains give us a trustworthy way to decentralize control and maintenance of a distributed digital ledger. This is achieved with three key design features. First, blockchains use distributed ledger designs that store multiple copies of the ledger locally. That's one of the features that makes it harder to attack the data. Second, anyone can run the software needed to store a ledger copy and validate new transactions. The rights to participate in these activities are permissionless. This permissionless access makes it possible to grow a decentralized network that is maintained by independent agents. Finally, game-theoretic designs are used to ensure that new transactions are proposed according to agreed principles, without the needs for agents to know, coordinate, or cooperate with each other. Historical ledger data is then secured using high-grade cryptographic techniques that make non-consensual data changes impossible with our best technology.